Myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of optical communication, we are moving towards the unit 3rd that comprises of the optical sources which are used in the optical communication, and here today I am dealing with the LED part 1. The content which to be covered in today's lectures are optical sources, LED introduction, LED drawbacks and advantage, material which are used for the fabrication of LED, and the different types of LED structures. So, first of all, what are the optical sources? So, whenever we talk about the optical communication, the main blocks which exist in the optical communication are first the transmitter section, receiver section, and in between optical fiber. So, here the block which I am selecting in this particular topic is the transmitter part of the optical communication, that includes the first block of the optical fiber. So, when we talk about any type of transmitter section, when the signals come to it, that signal is in the form of electrical. But in optical communication, when we talk about the optical communication, after this, the signal has to move towards the second block, that is our optical fiber, for the transmission purpose. And this optical fiber accepts the signal only in the optical form. So, here the signal is electrical and here the signal is in optical. So, we have to include something in between these two so as to convert the electrical signal into the optical signal, and that part is included in the transmitter part of the optical communication system, and that is our source, optical source. So, from the prime function of any optical source is to convert the electrical signal into optical signal. So, the optical signal is considered to be the active component because it is used for the generation of the signals. In optical fiber communication system, its fundamental function is to convert electrical energy into the optical one in an efficient manner which allows the light output to be effectively launched or coupled into the optical fiber. And it should be, first of all, its function is to convert the electrical energy into the optical one, and in such an efficient way that it can be easily, the optical energy which is generated from this optical source can be easily coupled into the optical fiber. So, two functions are performed by: first, conversion of electrical energy into the optical one, and the second one is the efficient coupling and the launching of this generated optical signal into the optical fiber. In broad way, there mainly consist of three types of optical source. First one, wideband continuous spectral sources, that is incandescent lamp, which are used earlier, but it has got a very little use nowadays. And the second one is the monochromatic incoherent light source, that is includes our light emitting diode LED, which is a topic of discussion in today's class, and monochromatic coherent source laser. So, the prime optical sources which are used nowadays are laser and the LED, and our today's topic of discussion is the LED. So, first is the incoherent and the coherent. We all have to know the meaning of these two. Incoherent means if the two signals are travelling and both of them are in opposite phase, then that two signals are said to be in continuation. It can be said to be incoherent source of light. That means the phase are opposite in the case of a incoherent, but in the case of a coherent source, the signals which are travelling parallelly have a in same phase. So, in coherent source add on to the total power, but incoherent source does not. So, here we are studying a incoherent source of light, that is LED. Now, before moving towards the LED, what should be the, first of all we will study about the what should be the major requirement for any device or any equipment or any component to be a optical emitter. So, what should be the major requirement? The first one, the size and configuration compatible with the launching light into an optical fiber. The size and configuration should be compatible with the launching light into the optical fiber, that is the light output should be highly directional. The second point, most accurately track the electrical input signal to minimize the distortion and the noise, and it should track the electrical signal more precisely so that the distortion and noise should be minimum. Ideally, the source should be linear. Should have emit light at wavelength where the fiber has. So, earlier we have seen that there are certain wavelengths where the attenuation and distortion or dispersion are less. So, the light should be selected, the wavelength of light should be selected in such a manner where we will have a low dispersion and losses. So, wavelength should be have low losses and low dispersion. Preferably capable of simple signal modulation over a wide bandwidth extending from audio frequency to beyond the gigahertz range. Simple signal modulation technique के लिए capable हो. Most couple efficient optical power to overcome attenuation in the fiber plus additional connector losses and leave adequate power to drive the detector. That means it should have a efficient capability of coupling with the other fibers. So, at the detector section we will have a adequate power so that the detector will able to detect that, because coupling process also leads to various type of losses and in a huge amount also in various cases. So, the sources which we will select should have a efficient coupling capability. Should have a very narrow spectral width. Already we have when we are dealing with the dispersion process, we have come across a term sigma lambda, and our dispersion is directly proportional to this sigma lambda, and this is our spectral bandwidth of a source. So, if we are saying that this spectral bandwidth is directly proportional to dispersion, so if we want to minimize the dispersion, we have to make it as narrow as possible. So, if we want to use any component or device as a emitter, optical emitter, it should be have a narrow spectral bandwidth in order to minimize the dispersion in the fiber. Must be capable of maintaining a stable optical output which is largely unaffected by the changes in ambient condition. That means the output should be generated should be have a stability. It is essential that the source is comparatively cheap and highly reliable so that it can be able to compete with the conventional transmission technique. Now, we are moving towards the LED, that is light emitting diode. That means, as the name suggests, that it is a type of a diode. LED. L stand for light, E stand for emitting, and D is the diode. So, what is the mechanism of light emission in this? The normally empty conduction band of the semiconductor is populated by the electron injected into it by the forward current through the junction, and the light is generated when these electrons recombine with the holes in the valence band to emit a photon. So, as the name indicates, that is a diode, that it should contain a PN p-type semiconductor, n-type semiconductor, and in between a junction. So what is going to be happen in this case? As per the during the forward current movement, electrons injected into forward current through the junction, and the light is generated when the electrons and holes combines with each other, recombine with each other, and which is generated by the p and n-type semiconductors. Light emitting diode are made very thin layer of fairly heavily doped semiconductor material, and depending on the semiconductor material used and the amount of doping, when forward biased, an LED will emit a colored light. What does it mean? That the light emitted by the LED depends upon the amount of doping. That is, doping means when the semiconductor exists, it exists in the intrinsic form, and when we add certain element, certain same types of elements on it, it become extrinsic, and the adding something to it is known as the doping process. So, heavily doped semiconductor material depends upon the doping and type of semiconductor material used. Which type of semiconductor material used decides the color which is emitted by the LED. Now, here is the main mechanism behind the LED function, how the LED function. So, the main process which is responsible for the emission of light from the LED is the spontaneous emission. So, what is the spontaneous emission means? Spontaneous emission is a process in which atoms returns to the lower energy level, and from where it returns to the lower energy level, that is from the higher energy level, it returns to the lower energy level in an entirely random manner, and this is known as the spontaneous process. It is a main reason behind the emission of photons in the case of LED. Photon is the responsible for the emission of light in the case of LED, and this is responsible in the case of LED with the help of spontaneous emission, which is a process of returning atoms from the higher energy level to the lower energy level in an entirely random manner. The random nature of the spontaneous process, where light is emitted by the electronic transition from a large number of atoms, gives an incoherent radiation. That already discussed in the first slide, that the LED give a incoherent radiation, that is having the different phase. Transition of an electron from the excited state, that is the highest state, to the ground state, that is state having the lower energy, happens as a result of natural tendency of electron. That's why it is called as the entirely random manner without the action of any external energy. We have always kept this in mind, that without the action of external energy, everything is happening here in the case of spontaneous emission naturally. No external agencies are involved for transition of atoms from the higher energy level, that is E2, that is the higher energy level, to the lower energy level E1. And when electrons moves from this higher energy level to lower energy level, what is happening? Photons are generated, which are responsible for the emission of light in the case of LED. So, important points are: no external energy are involved, everything is occurring naturally, natural tendency of electrons, and in the entirely random manner, and that is responsible for the emission of photon, which in turn responsible for the emission of light in LED. Now, drawbacks of LED in comparison with a laser. So, as we have told that it emits the incoherent light, that is why it has a lower optical power. That is why it coupled the lower optical fiber into the fiber as compared to the laser, which emit the coherent light. Lower modulation width, and here exists a harmonic distortion. Now, so this is not only the LED have got only the drawback, it has some advantage also. So, advantage of LEDs are its fabrication is simpler, because there is no mirror facet which exists in the case of a laser. Laser has a mirror facet for the is application, and it is a simpler fabrication. LED has a cost. Simpler construction of LED leads to the much reduced cost as compared to the laser. Reliability, the LED does not exhibit catastrophic degradation and has proved less sensitivity to gradual degradation than the injection laser. So, we can easily say that it is reliable also. Generally less temperature dependence. The light output against current characteristic is less affected by the temperature. Light output against the current characteristic. What output is obtained as compared to the current is less affected by the temperature than the corresponding injection laser, and LED does not has a threshold device, and therefore rising of the temperature does not increase the threshold current and above the operating point and hence halt operation. That is what does it mean? It does not exist a threshold, is not a threshold device, that is why rising the temperature does not increase the threshold current above the operating point and hence the halt operation. It is a very simpler device, that is why its drive circuitry is also simple. Simpler drive circuitry, this is due to the generally lower drive current and reduced temperature dependence, as we have discussed already, that is it is a reduced temperature dependence, and since the low power device, so the drive current is also lower in the case of a LED. Makes temperature compensation circuit unnecessary in the case of a LED, since it is a less temperature dependence, that is why temperature compensation circuit is unnecessary in this case of a LED. So, drive circuitry is also very simpler. Linearity, LED has a linear light output against the current characteristic, and already we have discussed in the important parameters which are required for any device to be an optical emitter, that it should be a linear, and LED fulfill that condition also. Now, we comes to the materials which are used for the fabrication of LED. Materials which are used for the fabrication of LED plays a very important role, because all types of materials can't be used for the LED. So, first of all, one thing is LED is a semiconductor PN junction diode. So, it is not important that all the semiconductors can be used for the fabrication of LED. All the semiconductors can't be used for the fabrication of LED. There is a special type of semiconductors which are used for the fabrication of LED and which we will discuss here. LED are comprised of compound semiconductors, that is Si and G, that is silicon and germanium, which are general semiconductor, which we knew does not, because it is not a compound semiconductor. So, they can't be used for the fabrication of LED. In the fabrication of LED, we use the compound semiconductors which are made from the group 3rd element and group 5 element. For example, gallium arsenide GaAs and gallium phosphide GaP. So, it is a compound semiconductor which are made from the group 3rd and group 5 materials. The increased concentration of minority carrier in the opposite type region in the forward biased P and diode leads to the recombination carrier across the band gap for a direct band gap. So, as we know that there exist two type of semiconductors, direct band gap and the indirect band gap semiconductor. Direct band gap semiconductors include gallium arsenide and gallium phosphide, which we are seeing here. So, we can easily say that for the fabrication of LED, we use the gallium arsenide and the gallium phosphide, and indirect semiconductors are silicon and germanium. So, they are not used for the fabrication of LED. So, what is the difference which exists in these two types of semiconductors, that Gallium arsenide can be used as a for the fabrication of LED, but silicon and germanium can't be used. So, here is the difference. When we see the structure here, what is that? This is a structure of a direct band gap and this is the structure of indirect. So, when we see this diagram, the upper level of the valence band and the lower level of the conduction band. In between the valence band and in between the conduction band also different types of energy levels exist. So, we can say upper energy level of the valence band and the lower energy level of the conduction band should have a same momentum or the wave factor. Again I am repeating, in the case of a direct band gap semiconductor, upper energy level of the valence band and the lower energy level of the conduction band have the same momentum or the wave factor. That is why the transfer of electron and hole, that and also we can say recombination process is very much easier as compared to the indirect band gap, and that will lead to the release of photon. But here it is not at the same level. In order to increase electroluminescence, it is necessary to select the appropriate semiconductor material. The most useful material for this purpose are direct band gap semiconductors, in which electrons and holes on either side of the forbidden energy, it is the forbidden energy gap, electrons and holes, this is the holes and this is electrons, have the same value of crystal momentum, have the same, they are in the same, and thus direct recombination is possible. So, this is the difference why we can't use the indirect band gap semiconductors for the fabrication of LED. And here it may be observed that the energy maximum of the valence band occur at the same value of the electron crystal momentum as the energy minimum of the conduction band. Already we have seen in this in the figure. Hence, when electron hole recombination occurs, the momentum of the electron remains virtually constant and the energy release. So, when the electron hole recombination occurs in the case of band, the same direct band gap, the momentum of the electrons remains the same and the energy is released, which corresponds to the, of course, the band gap energy between the conduction band and the valence band. So, there is a difference here. We can see that this is a direct and these are the indirect, and we can have the energy band gap and recombination coefficient. So, we can see that recombination coefficient in the case of direct band gap is higher as compared to this indirect band gap. That is why this will lead to the energy emission in the form of a photon. Now, double heterojunction LED. Now, till now we have discussed about the homojunction LED. Homojunction LED, that means the P and N type of semiconductors which exist in the LED are made up of same material, but the heterojunction LED means there exists in another material in between P and N type of the same material. So, what is happening here? If we have a P and N of the same material, and if we insert another material, for example, we take it X. So, there exists first junction, and this is a junction between two different material, and again exists this junction, and this is also a junction between two different material. So, double hetero junction. Hetero means different and double means two. So, two and different junction LED. The device consists of a p-type GAS layer, this p-type GAS layer and n-type GAS layer sandwiched between a p-type aluminum gallium arsenide, and this X which I am taking in this picture is aluminum gallium arsenide. So, this is of course a difference because the P and N of gallium arsenide. When a forward bias is applied, electrons from the N-type layer are injected through PN junction of what? P-type gallium arsenide layer, where they become minority carrier. This minority carrier diffuse away from the junction, recombining with the majority holes, and this therefore photons are produced with energy corresponding to the band gap energy of sandwich layer, which is our P-type gallium arsenide layer. The electroluminescence occurs only in the gallium arsenide junction, providing both good internal quantum efficiency and high radiance emission as compared to the homojunction one. Light is emitted from the device without reabsorption because the band gap energy in the aluminum gallium arsenide layer is large in comparison with the gallium arsenide. The DH layer, that is double heterojunction structure, is therefore provide the most efficient incoherent source of light as compared to the homojunction LED. This is a structure. Here we have taken aluminum gallium arsenide and aluminum gallium arsenide, and in between sandwich layer is the gallium arsenide, and energy band diagram, and this is the emission of photon. Now, we are going to discuss about the different LED structure. The basic one is the planar LED. It is the simplest of the structure that are available and is fabricated by either liquid or vapor phase epitaxial process over the whole surface of the gallium arsenide substrate. This involves a P-type diffusion into the N-type substrate in order to create the junction P-type in between the N-type substrate forward, and so the junction is formed between this P-type and this N-type, and forward current flow through the junction. When the junction is formed, the forward current flows, which gives Lambertian spontaneous emission, and the device emit light. This is the simplest form of a PN junction diode in the form of an LED, which can have the capability to emit light. This is one of the important type of a LED, that is surface emitter LED. It is a method of obtaining, and why it is used? It is used for obtaining the high radiance, restrict the emission to a small, and how this high radiance is obtained? By restricting the emission to a small active region within the homostructure device. This is the homostructure device, and we are actually limiting the active region. We are taking the small active region for obtaining the high radiance. With homostructure device and each well, you can see here that here exists a each well is each created in a gallium arsenide substrate. This is the N-type gallium arsenide, and the well is eached in order to prevent heavy absorption of the emitted radiation and physically to accumulate the fiber. This structure have low thermal impedance in the active region, allowing high current density and giving high radiance emission into the. So, instead of the complete this much structure, we are restricting the active region till this only, and this will allow the, so density will increase. If we decrease the area, density of current of course decreases, and this will lead to the high radiance emission, and the fibers get coupled into this each well. Now, the second type is the edge emitter LED. So, this device is a similar geometry to conventional contact distributed injection laser. The geometry is similar to that one. It has an advantage, it takes the advantage of transparent guiding layer with a very thin active layer, in order that the light produced in the active layer spread into the transparent guiding layer, reducing self absorption in the active layer. Most of the propagating light is emitted at one end phase due to the reflector on the other end phase and the anti-reflection co-emitting on the emitting and the phase. So, this is also an important type of LED, and the difference between the surface LED and the edge emitter we will discuss. Surface emitter, it emits from the upper, and the edge emitter, it emits from the edges. So, this is a basic difference. Also, there exists a difference between its radiation capability and the coupling capability, which we will discuss in the last slide of this particular session. Now, this is a very simplest form of LED which we see in our daily life, that is dome shaped LED. It is of hemisphere of N type GS around the P type region, high external power efficiency than the planar LED, which is also one of the simpler one, but not more than the surface or edge emitter LED. Then this is also one of the simplest form of this is also one of the form of an LED, that's not a simplest one, and superluminescence LED, and so it provides an output power equivalent to laser diode. Its output power is equivalent to laser diode and a wide oscillation spectrum equivalent to LED. Basically, this superluminescence LED comprises the advantage of both laser and the LED. It emits light with a narrow active layer equivalent to a laser diode. Its property is also similar to the laser and the LED. And this is a resonant cavity LED, uses photon quantization in microwave cavities to enhance spontaneous emission properties, directionality, intensity and the purity. Now, there exists a comparison between the surface and the edge emitter. Effective radiance at the emitting end phase can be very high, giving an increased coupling efficiency into a small numerical aperture of the fiber compared to the surface emitter. So, we can say that edge emitter has a better coupling capability than the surface emitter. Surface emitter generally radiate more power into the air as compared to the edge one. Edge emitter also have been found to have substantial better modulation bandwidth than the surface one, and it is possible to construct the edge emitter with narrower line width so that the dispersion can be reduced than the surface emitter. So, with this I am going to end the first part of the LED section. Thank you for attending class.